Topological data analysis is concerned with finding the underlying shape of a dataset. Often, a union of balls called offsets is used to approximate the shape and fill in the space between points. The topology of the balls can be represented discretely by a simplicial complex called a nerve. Every subset of balls with a common intersection contributes one simplex to the nerve, an edge for each pairwise intersection, a triangle for each three-way intersection, etc. Instead of looking at just one radius, we can look at the offsets of all radii from 0 to infinity. A growing space like this is called a filtration. The nerves give a corresponding simplicial filtration. Persistence barcodes describe the change in topology in the course of a filtration. They mark the components, holes, and voids as well as their lifespans. Here's a 2D example. Simplicial complexes on large datasets can become very large very fast. Several recent papers describe efficient sparsification techniques. In this video, we illustrate a geometric perspective on sparse filtrations that leads to simpler proofs, more general theorems, and a more visually immediate explanation. At larger scales, fewer points are needed to give a good approximation. The two offsets are close, but the one on the right uses many fewer points. The goal is to remove points as the scale increases. Note that removing a ball may cause a union to no longer be a filtration, because filtration should only grow and never shrink. However, removing a completely covered ball doesn't change the union. By limiting the radius of points to be removed, we can guarantee that the ball is covered at the time it will be removed. If we visualize the scale parameter as another dimension, a growing ball traces out a cone. This cone is modified in two ways. First, we assign a maximum radius to each point. Next, we truncate the cone at the height when the point will be removed from the filtration. The maximum radii and height are chosen so that the top of the cone is sure to be covered at the time it's removed. This corresponds to the covering property described earlier and can be seen in the example by the green cone covering the top of the truncated red cone. These cones give a new filtration one dimension higher. The sparsified union of balls is the level set filtration. Flattening the union of cones to the union of balls doesn't change the topology. This projection is a homotopy equivalence, and so the cones and the balls one dimension lower have the same persistence diagram. The nerve of these growing cones is the desired sparse filtration. The persistent nerve lemma implies that the nerve filtration has the same persistence barcode as the union of cones. This is simpler than previous approaches because it delays the switch from geometric to combinatorial objects. It is much easier to prove a ball is covered by a nearby ball than it is to prove that the removal of a vertex doesn't change the homology of the simplicial complex. Also, there is no need for zigzag or simplicial map persistence in the algorithm or its analysis. This geometric perspective is more general because it applies to any convex metric, notably L-infinity, which includes the popular Rips filtration. We hope this geometric view makes sparse filtration both easier to understand and use.